the last time out we just had a look at the various sections of this C-Sound file. Okay, so today we're going to just look at these in a little bit more detail, and I'm going to try to introduce to you some of the concepts and some of the way C-Sound, the language works itself. Okay, it's kind of ambitious to do in a 5-10 minute video, but maybe it's enough to get you started or interested, or give you kind of an overview of how things kind of generally go together in C-Sound. So to do that, we're going to just kind of focus the attention of this session on this block of code here. Okay, so this block of code is an instrument block of code here. Okay, now it's instrument 1, okay, which is kind of important because that means that by default Cabbage is going to trigger that instrument each time we play a note. Okay, why does it do this? It does this because C-Sound is set up in a particular way to trigger instrument 1 with any notes that are coming into MIDI channel 1. So it's kind of neat to have this kind of setup. I could also call this, I could also give it a name. I could call it simple synth. I'm just going to leave the number beside it as well, so I can give it a name and a number. So we have this instrument called simple synth, and it's going to be instrument number 1. Okay, so like I said, you're as well off to use a number for an instrument if you're using Cabbage, because it just kind of makes things a little bit easier, because we know that every time we play a note on this keyboard, it's going to trigger instrument 1. If we wanted to do some kind of program change, we could have instrument 2, and then we could have some kind of program change button, and then it'll play a different synth on instrument, or when we change the program, when we start sending notes to MIDI device or MIDI channel 2. Okay, so what's happening in this code then? This is the next bit. Okay, so we've got our instrument block, which always starts with an inst and ends with an end in. Okay, if you leave out an end in, you're going to get some errors. So for example, if I take this out and I save this, we've got some errors that appear down here. It says error unexpected end token from blah 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 line 22. Okay, so some of these output messages can be a little bit cryptic, but it's basically, it says that there's an error in line 22. That's because this hasn't been closed and it's coming all the way down to the end of the orchestra section. So it'll take a while to get used to the actual error messages that you see in C-Sound, but once you can identify them, it's going to help you speed up development of your plugins. Okay, so next, so what happens when we play this instrument? Okay, so when we play this instrument, let me save that because I didn't save that. Well, that's the other thing. Okay, every time you make a change, change some text in Cabbage, you need to save it before it's updated. Okay, so I didn't get any sound there in the last instance because I had an error, but I hadn't saved the edit that I'd made. So back to sound. Okay, when you hit play on the keyboard, this instrument is going to be triggered. Okay, and if we take a very simple view on this, we can say that for as long as we've got a note held over here, this instrument is going to be, the text in this instrument, C-Sound is going to loop through this instrument, well, basically say 44,100 times a second, or whatever the sample rate is. Okay, so it's going to keep executing this code in a very high resolution and very quick loop. And basically it's going to get to kenv, and it's going to read this, and then it's going to get to this line of code, it's going to read this, and then it's going to get to this line of code, it's going to read this and do something, and then it's going to start back again at kenv, and it's going to update that, and so it kind of goes in a loop. So what happens in that loop? The first thing we have is we have this kenv. Okay, so this, well, we'll start with this. Okay, MADSR is an opcode, right? And opcodes in C-Sound, they do things like functions or methods that you might see in other languages. So the opcodes always have inputs on the right hand side and outputs on the left hand side. Okay, so you're always going to have, for almost all opcodes that you see in C-Sound, you're going to have outputs are going to be on the right hand side and inputs are going to be on the left hand side. So you've got your inputs over here, you've got inputs to VCO over here, and you've got inputs to outs on this side. Now the thing is, outs doesn't have any outputs, it only has inputs. VCO has outputs and inputs, or VCO2. MADSR has inputs and it has an output. Okay, so when we use opcode, we first of all we declare it's if it has an output, we declare a variable that's going to be that the output is going to be assigned to. Okay, in this case we're going to call this kenv. Okay, so this is a k rate variable, right? So what are variables? A variable is it's basically a location on, or it's basically a little bit of memory on the computer's RAM, and the values in that can change and update over time, and that's what happens every time we run a C sound instrument. Kenv is going to be updated several times a second, Out is going to be updated many times a second, and the resulting signal is going to be sent to the sound card. So for MADSR we've got 3 inputs, so we'll talk about the KN bit, the output, in a moment. We've got 3 inputs, so an ADSR envelope kind of looks like this. The first input, we call these also input arguments, so the first input argument is 0.1, okay, and that tells us that there's going to be 0.1 of a second between the start of this sound and the time it gets to the full amplitude. Okay, it's going to be 0.2 of a second between the top of the attack and the decay. So this is going to be 0.2. This is terrible. It's very hard. I'm left-handed. I'm using a mouse right-handed, so I think it's pretty impressive I get this far. Now the 0.6. So the 1 relates to this. The 2 relates to this. That's a terrible 2. Anyway, and 0.6 is the only input that doesn't relate to time. It relates to this value here, which is the sustain level. And then 0.4 is going to relate to this, the amount of time it takes for the sound to die off. So when we play this note, it's going to take 0.1 of a second to get to full amplitude. It's going to then, in 0.2 seconds, drop down to the level of sustain, which in this case is 0.6. And then it's going to tail off, and it's going to take, as soon as we release the note, it's going to take 0.4 of a second to die away. So when we play this, so for example, if I change this to, whoops, didn't mean to do that. If I change this to 4, for example, and I update this instrument and I play it, it's going to take 4 seconds for the note to die away once I release the note. So I'm going to play the note, I'm going to release it. It takes 4 seconds to die away. So that's your ADSR. I mean, they're kind of a major component in almost all synthesizers that you're gonna use. So the next thing is then the kenv. Okay, so kenv is the output of this ADSR, right? So that means while this instrument is playing, kenv, the variable kenv, is going to be assigned values depending on what stage we're at in our ADSR. So for example, if we happen to be at this stage here, then kenv is going to be 1. If we're at this stage, kenv is going to be 0.6. If we're anywhere along here, kenv is still going to be 0.6. If we're here, kenv is going to be 0. It's going to be the end of the note. Okay, so kenv is a variable, and it's going to be continuously changing over time. Okay, but basically, as with any variables in C sound or any languages, usually they just refer to some kind of numerical data. So, and then it's the same here. So kenv is just going to refer to some numerical data. Now we can use kenv elsewhere, and you'll see it being used down here. Okay, but the next thing we have is Out, and we have a VCO2, and then VCO2 has 2 inputs. Okay, so the VCO2 has 2 inputs, and they are P5 and P4. Okay, so those inputs are related to what we have up here, to the, well, I'm not going to rub that out because it's going to take me too long, to this. So we've got MIDI key CPS is equal to 4. Okay, now VCO2 is voltage control oscillator. It's going to generate a sawtooth waveform, which is what we hear every time we play this instrument. Oh, still 0.4 seconds, or it's still 4 seconds long. That's better. Okay, so actually I put that there, now we can't see that. So MIDI key CPS equals 4. That means every time we play a note on the keyboard, P4 in instrument 1 is going to be essentially replace the value, well, it's going to be, yeah, let's just say P4 is going to become the value of the MIDI note in cycles per second. So the frequency, of the MIDI note. So for example, that's 261 hertz. So P4 is going to be 261 hertz when that note is pressed. Okay, when A440 is pressed, it's going to be 440 hertz. Okay, similar with P5. That's going to be a velocity amplitude from the MIDI keyboard. So we can see that this basically relates to this, and this is going to relate to this P5. And it's going to be velocity amplitude between 0 and 1. Okay, so the louder we play the keyboard, for example, in Cabbage, if we play down here, it's quite low and gets louder and louder and louder and louder and louder and louder, and eventually it goes to 0.1. Again, we can see these things if we print out, if we just use a print opcode and say print P5 and then do print P4. I'm going to save that, and now when we play, we can see the values appear down here. So we can see P4 is 0.8. If I play at the very bottom of it, P4 should be almost 1. It's 0.978. Okay, and we can see the value in hertz coming through there as well. Okay, so this is a quick and simple way of sending information, note and amplitude information to our instrument each time we play it. Okay, and finally we have the outs opcode, which takes a variable, or which takes, well, in this case it's out S, so it's out stereo, so it takes 2 input arguments. So that's the first input argument, in this case A out multiplied by K env, and then A out multiplied by K env again. Right, so in this case what we're doing is we're taking the output of the VCO2, which is going to be a series of numbers that represent a sawtooth waveform, and we're going to multiply them by the value of K env. So K env is a time variant value, it's changing over time. So we're basically going to shape the amplitude of the output by multiplying it by the ADSR. Okay, that's the basis of what's happening here. To go in a little bit more detail, the difference between a K rate variable and an A rate variable is that the A rate variables are going to be updating much quicker. So the A rate variables are basically going to be updating, they're going to have 44,100 samples each second, whereas the K rate variables might have much less than that. Now, this is all determined by something called KSMPS, which is defined up here, which sets the number of samples in every control period. Okay, so, or every K cycle. So what happens is basically when Csound runs, all the K rate variables are going to update, let's say like this, at this rate. So you get to update, update, update. And then all the audio samples are, let's just actually set this to 4. And then we'll get a better description here. So all the audio samples when KSFPS is equal to 4 are going to be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1. So they're going to be updating 4 times in every, so for every time the K rate variable updates, there's going to be 4 updates to an audio rate variable. Okay, which brings up another thing, and that is that K and K rate variables are scalars. They're always just one value, right? If we stop the execution of Csound and we look at a K rate value, it's just going to be one value. If we stop the execution of Csound halfway through and pause it somehow, and we take a look at an A rate variable, we'll see that it's actually a vector. Okay, so it's going to be a vector of values. So it's going to be a vector, not a Euclidean vector, but a computer science vector, which is like a series of numbers. Okay, so what happens is on every K rate cycle, Csound is going to generate KSMPS audio samples. Generally then this is going to be sent to the output, so this is kind of block-based processing, similar to the idea of buffers basically that you have in DAWs. You know, you can set the buffer size, and that sets the number of samples that are going to be processed before sound goes to the speakers. One other thing then in this whole mess is I-rate variables, which we haven't looked at. So I-rate variables are kind of, so we looked at K-rate variables and looked at I-rate variables. I-rate variables are a special type of variable. They're called initialization variables. And the nice thing about them, well, no, they're just, I mean, all variables are nice. Let's not be derogatory towards any variable type. That wouldn't be fair. iFreak, in this case, so we're going to set up this variable called iFreak, and it's going to be assigned the value of P4. So I-rate variables can be updated only between notes. They can't be updated during a note. Okay, so for as long as I press it, so if I save this, for as long as I'm holding this note, iFreak is going to be fixed in value. It can't change. Okay, so we've seen obviously KEnv is constantly changing, because when we play the note we can hear there's an attack and there's a decay and there's a sustain and then there's a release. So we can see that KEnv is a value that changes over time. iFreak is fixed. It doesn't change over time. so it's fixed. But it can change between notes, between instances of an instrument. So in C Sound Speak, every time we trigger an instrument to play, we're creating an instance of that instrument, and we can have multiple instances of an instrument happening at the same time. For example, if I can play this with the MIDI keyboard or with the computer keyboard, so I can play 2 instances of that instrument at the same time. So we have kind of polyphony out of the box, which is one of the nicest features of C Sound, and it's something that other audio languages you kind of have to wrangle with a little bit to get polyphony, but we have that in C Sound. Okay, yeah, thus concludes that particular video tutorial and introduction to the C Sound syntax. So in the next video tutorial, we're going to look at implementing some of the features that can be found in the Korg Monotron synthesizer, which is this, which is basically, it's a nice little simple analog subtractive synthesizer. So we're going to try and model some of the features that are found in that in the next video. Thanks for watching. See you. Bye bye.